elementary plane flow solution. The present chapter is a detailed introductory study of inviscid incompressible flows, especially those that process both a stream function and velocity potential. Let me write incompressible inviscid flows or inviscid flows, especially those that process both a stream function and velocity potential. Many solutions makes use of the superposition principle, so we begin with the three elementary building blocks were also illustrated in the picture below. A, which shown also here, a uniform stream in the x direction, B, a line source or sink at the origin, and C, a line vortex at the origin. This type, sink or source, a line vortex, at first we are going to formulate part A, which is uniform stream in the x direction. A uniform stream V equals to, as shown also in this picture, A so we have two components. We had previous for two components for psi and phi. For phi we had this relation, which was equal also to this relation, and for minus so at the next, let me write again. We have U equals which was equals to and component related to v equals to 0, we can have a relation here phi equals to u x plus c, for example, and psi equals to u y plus c 1 and c2. We may integrate the expression and discard the constant of integration. If we discard the constant integration, we can finally have a relation for a stream function, which is and phi ux. The stream line are horizontal straight line. Let me show here. U and the potential line are the vertical x constant psi and the for perpendicular to phi and psi are perpendicular to each other. The next typical problem was the line source or sink at the origin. Suppose that the z-axis were a sort of thin pipe manifold through which fluid issued at the total rate q uniformly along its length b. So with q volume fluid, uniformly along its length thin pipe manifold looking at the xy plane, we would see a cylindrical radial outflow or line source. So in xy direction, xy plane, we have cylindrical radial outflow or line source. As shown, also can be shown as this picture. Figure B. Plane polar coordinates are appropriate and there is no circumferential velocity at any radius, or the velocity is, so we have, in this case, we have radial flow which VR equals to the volume flowed from the sink or source to the sink or from the source on the area, which can be equals to M on R, where M Q on 2 pi B. At the end we have this relation for VR, M on R. From previous we had for the polar coordinate for psi and phi, we had this relation for psi, and for phi now we can calculate, and also v theta equals to 0, where we have used the polar coordinate form of the string function and the velocity potential. Integrating and again discarding the constant of integration, we can obtain the proper function for the simple radial flow, which are for psi m theta, and for phi m on r. Phi equals to integration of m on r dr, which equals to m ln r. So we can write phi for the source or sink where, as we said before, m equals to q on 2 pi b, positive for source and negative for sink. As shown on the previous picture, the streamlines are radial and the potential lines are the circuits. Example, consider this point. You have streamlines and potential flows phi for the sink or source. The next, elementary plane potential flows are line irrotational vortex. A two-dimensional line vortex is a purely circulating steady motion. Let me write. Line vortex is a purely circulating steady motion. Steady motion where v theta equals a function of radius only and Vr equals to 0. This satisfies the continuity equation identically as can be checked previously or now. We may also note that a variety of velocity distribution satisfies the theta momentum equation of viscous fluid. We may show as a problem exercise that only the one function is irrotational. That curl v equals to 0 and v theta on R where k is a constant. This is sometimes called a free vertex. For which the stream function and velocity may be found from these relations. Vr, as is said, on psi is opposite of the derivation variable and phi have the same variable derivation, and for theta also we have this relation. Opposite, we have theta v r, and for phi we have same derivation of the component with integration and eliminate the constant. We can obtain psi and phi where k is a constant called the strength of a vortex. As shown also in this picture for a vortex. C the streamline are circles, stream where in the sink or source the streamlines were arrows in the radial direction, but in the vortex the streamline are circles and the potential perpendicular to the streamline is radial spokes. Potential line constant theta. Note the similarity between these equations and the previous equation. A free vertex is a sort of reversed image of source. So we can write a free vortex is a sort of reversed images of sources. Sources. The bad vortex formed when the water drains through a button hole in a tank is good approximation to the free vertex pattern. So let me write an example. The bad vortex. This is the end of this section. The next section is about superposition of various elementary flow patterns.